Yeah, welcome back to Toronto Air Seminar. And today's talk will be developed by Weiyu Liu. He is a robotic PhD candidate at Georgia Tech in the School of Interactive Computing, working with Professor Sonia Chernova. He studies the representation and reasoning of semantic knowledge for robotic manipulation. His research unites symbolic knowledge and robot sensorimotor data through the use of relational and multimodal machine learning, enabling novel domestic robotic applications such as knowledge-guided object search, context-aware grasping, and language-conditioned object rearrangement. Prior to his PhD, he earned his bachelor degree at Georgia Tech in electric engineering in 2017. He has worked at the NVIDIA AI Robotic Research Lab during his graduate studies. Yeah, Weiyu, take it away.
All right. Thank you so much, Reinhard, for the introduction. Thanks for having me at this seminar. Let me share my screen. Oh, move back one slide. All right. Sorry. All right. Thank you, everyone, for attending. Thanks again for inviting me. Today, I would like to discuss my work on grounded semantic reasoning for robotic interaction with real-world objects. So the question that drives my research is, how do we develop autonomous robots that operate in human environments? This requires the robot to manipulate novel objects while adapting to changes in tasks and also environments. One idea that has been around for a very long time is to develop, for developing such intelligent system is to use knowledge and also semantic representations. And there are several crucial components in this approach. The first component is semantic representation. They allow robots to encode the common sense knowledge that every human beings know about the world, ranging from physics to functionality of objects to aesthetic to individual preferences and also social norms. Semantic representation also provide a data structure and an abstraction that the robot can manipulate more efficiently. For example, instead of modeling the complete 3D geometry of this pair of scissors, we can decompose it into the blades and also the handle, which allow us to generalize to other objects. Another example is this table setting. We see that we can decompose this complete structure into substructures that are semantically meaningful, such as the stack of plates, the utensils on both sides of the plate. Practically, however, we cannot provide robots with all the knowledge about the world or manually specifying structures for different problems. Therefore, another thing that's very important for the robots to achieve is the ability to reason about what is implicitly represented in the subbody of knowledge that they have access to. And one example is deductive reasoning. However, there are so many different computational frameworks that support different kinds of reasoning, such as logic, probabilistic graphical models, and also more recent graph neural networks and transformers. Combining knowledge representation and reasoning has enabled many successful robotic applications, particularly for high-level tasks, such as language grounding, semantic mapping, as well as robot interaction and task planning. However, a crucial challenge for applying semantic reasoning to robotic perception and manipulation of objects is to closely connect the symbolic representations, such as structured knowledge graph, as well as textual facts, with robots' sensorimotor data, such as object point clouds, 6-off poses, spectroscopic readings of object surfaces. Also, this problem is also known as the symbol grounding problem. This integration is hard because these two types of data have drastically different characteristics in terms of modality, granularity, and also diversity. So there is continuing efforts in making symbol grounding compositional, more active, and also multimodal. However, we should not stop at mapping invariant features in the sensorimotor data to predefined categorical representations. Instead, we should develop a deeper interaction that reveals the meaningful patterns of object properties and also uses. And to achieve this goal, I propose to connect sensorimotor data with semantic knowledge with using reasoning. Specifically, we want to reason about multimodal data within a unified semantic representation. We want to reason about the symbolic concepts and sensorimotor signals together. We also want to reason at different levels of abstraction, from very specific sensorimotor data to more abstract semantic high-level knowledge. So to put these ideas into action today, I want to discuss 3 projects on semantic reasoning for multimodal perception, grasping, and object rearrangement. For the first project, we are motivated by the task of multimodal interactive object perception, where robots can use different exploratory actions and sensors to detect semantic properties of objects, such as absorbent, fuzzy, smooth, sticky. Understanding these properties aids robot in performing many real-world tasks. Many more properties can be extracted from this approach using different sensorimotor signals. However, existing research in object perception often develops separate algorithms and also specialized sensors for detecting different properties without modeling the relations between these properties. Existing knowledge representation of objects, however, is not enough for this job. Prior work has primarily encoded the pairwise relations between an object's class label and its semantic properties. For example, cup is made of glass, cup has the property fragile. Such representation does not take full advantage of robots' multimodal observations. For example, in this pairwise setting, detecting that the cup is clean does not help the robot to infer whether this cup is more likely located in the cabinet, sink, or refrigerator. Therefore, our goal is to enable robots to collectively reason about all the different object properties, particularly ones that can be grounded in robots' sensor modalities. We want robot to answer questions such as, should a cup be stored in a cabinet? Is a thick brown bowl more likely to be made of metal or wood? Specifically, we make 3 contributions. We first introduce a novel representation to model these relations. We then collect a new data set and also propose a new computational framework based on the transformer neural network. First, we propose to use n-ary relations to model the interrelated object properties. Each n-ary relation can be expressed as a set of row value pairs, where each row corresponds to a specific object property type and the values correspond to the property. These n-ary relations are very intuitive to us humans. For example, one n-ary relation can be a dirty ceramic cup is likely to be located in the sink. Use this n-ary relations also allows the robot to reason at different levels of abstraction. For example, without additional information from the sensor, the robot can perform class-level inference to identify both the sink and cabinet as likely locations for a cup. Given additional information, such as that this cup is clean, the robot can use the n-ary relation to predict that cabinet is a more likely location for this clean cup. However, a key challenge for using this n-ary representation is to collect semantically meaningful n-ary data. In other words, we need to know how often do various attributes and properties co-occur. Unlike binary relations, which can be created by experts or crowdsourced, n-ary relations are very difficult to construct manually at scale. So our solution is to learn generalizable n-ary relations from observations of object instances, each representing an identified set of object properties for a specific object instance situated in a particular environmental context. Some examples are shown here. We use a multi-step crowdsourcing process to collect this data. However, this data can also come from the robot as well. As the robot interacts with more objects in the environment, it can leverage its experience to build a more accurate model of objects. Here is a summary of the properties we model in our work. These properties include both immutable properties such as class, material, color, as well as mutable properties such as dampness, cleanliness, as well as locations. Using these properties, we contribute a semantically rich dataset consisting of 1,457 object instances. For each situated object instance, we have a complete annotation. And here are some more examples from our dataset. We see that although these objects are all cups, they have different physical properties. They also have different potential uses and also suitable locations. So our next challenge is to build a reasoning framework that can go from the specific n-ary relations, the n-ary observations to more generalizable n-ary relations. For that, we introduce a neural network model based on the transformer, which has shown to be very effective at capturing order distributional information in language and computer vision data. Our transformer takes as input embeddings of properties observed from an object instance and builds a contextualized embedding for all the observed properties. This contextualized embedding is then used to predict the unknown properties of this object instance. We modify the original transformer neural network to remove the positional embeddings, allowing this model to be permutation invariant to the order of the properties, because there is no canonical order for object properties. To train our model, we randomly replace a single property from an observed properties of a situated object instance with the mask token and request the model to reconstruct this hidden property. In this example, we request the model to reconstruct the location of this blue cup in the sink. Trained with this self-supervised auto-encoding objective on different properties, as well as different object instances, the model will learn statistical rules that is universal and can apply to different objects, such as small objects made of paper is usually light. Dirty objects that are made of ceramic should be washed in the sink. So using this kind of generalizable n-ary knowledge, we want to predict unknown properties of novel object instances. We compare our method with 5 different baselines, and we report mean reciprocal rank and hits at k. Some of these methods model binary relations directly. Some methods approximate n-ary relations with binary relations. Co-occur is a binary model learning co-occurrence frequency between object class and properties. So this is this is the same as the binary representation we discussed in the beginning. Tucker is a binary knowledge graph embedding model. Tucker Plus is the model, is the binary knowledge graph embedding model approximating n-ary relations. And NALP is a state-of-the-art n-ary knowledge graph embedding model. Markov logic network MLN models indirect relations between all possible pairs of object properties. So we see in this comparison that comparing to the Markov logic network, which is the previous state of the art, our method shows significant improvement in performance while reducing computational time by more than 150 times. This drastic reduction in inference times allow our model to be used by robot to reason about object properties in real time. We also validate our method in a real-world robotic task where the robot needs to predict locations and rooms of objects based on a sparse set of properties that human users would normally provide, such as find me a clean glass cup or find me a cold beverage. This experiment also validates our model with a different set of users than the users who help us constructed the data set. Compared with the baselines, our model is able to kind of close the gap to the human level performance at retrieving objects from users' top 3 locations within 1 try, 2 tries, or 3 tries. We also demonstrate the qualitative improvement. Equipped with our model, the robot is able to find objects considering different properties of the object. In this example, the robot searches for the dry sponge on the kitchen counter and in the kitchen drawer, while it tries to find this wet sponge in the kitchen sink. So in summary, in this work, we introduce an n-ary representation to model the higher order relations between object properties, and also the diversity of environmental contexts for objects in the real world. We further demonstrate that the use of semantic representation enables robot to unify information from different sensor modalities, and this approach can be potentially used for guiding active multimodal perception. Next, we will see how semantic understanding of environmental context can help robot grasp and manipulate objects. So in this second project, we focus on the problem of semantic grasping. Unlike classical grasping, which mostly concerns with stability and speed, semantic grasping is the problem of selecting stable grasps that are functionally suitable for specific manipulation tasks. This is very similar to how humans grasp objects. We do so with the clear purpose of preparing the object to be used for an intended manipulation task. For example, when we grasp a mug full of hot coffee for drinking from it, we use the handle even though other stable grasps exist. We develop a novel framework we call CAGE, context-aware grasping engine, to reason about the broader range of contexts for achieving purposeful robotic grasping, including object affordance, material, state, and task. To capture the environmental context, we extract semantic representations from sensor data. We use the point cloud of the object to first sample antipodal stable grasps. We also use the spectral reading from the silo sensor to detect the material of the object. We then identify the state of the object as well as the subsequent manipulation task from the user instruction. Using RGBD image of the object, we also extract affordance segmentation of the object. In this example, we see that the object is decomposed into the part with a support affordance and also the part with the grasp affordance. This affordance segmentation can generalize to different object classes and also instances. In particular, we see in the bottom row, the contain affordance is shared between the spatula, the pen, and also the bowl. However, I want to mention here that this affordance segmentation is based on visual appearance of object alone. Therefore, it does not consider other factors. For example, if we want to use the spatula for poking and or stirring, we should not grasp the part even though the part has the grasp affordance, right? So our model is trying to reason about these higher order affordance. So come back to this model. We combine all the information extracted from the sensor data to build a semantic representation of this context-dependent grasp, which we denote X here. Our goal next is to predict Py given X, where Y is a variable indicating whether this grasp is suitable for this context or not. We use a wide and deep neural network in the work to reason about these semantic features together. However, we can also substitute it with the transformer neural network we discussed earlier, so I will skip the details here. For evaluation, we collected a semantic grasping dataset, SG14000. Different from existing grasping dataset, this dataset captures the diversity of contexts a robot may encounter in real life. We benchmark against 3 baselines on finding suitable grasps in novel contexts. CA ignores any contextualized information at all. Frequency table of affordances, FT, learns co-occurrence frequency between tasks and grasp affordance. Classification of visual features, VF, grants semantic grasp to low-level visual features. And we use standard metric average precision to evaluate the predicted ranked grasps. There are several takeaways from this comparison. Comparing with CA, we see that it's very important to consider object affordance, material, and other contexts for purpose for grasping. Comparing with FT, we see that affordance based on visual appearance alone is not enough to capture the changes of or the dependencies of object functionalities on other factors. Comparing with VF, we see that semantic features offer the opportunity to unify contextual information extracted from different sensor modalities and provides an abstraction that can possibly promote generalization. We evaluated the effectiveness of our method on a fetch robot. From this video, we see that the robot is able to grasp an object differently by considering the task. Other contextual information, such as the state of the object, also influence grasp selection. Finally, we see that semantic grasps can be generalized between object instances and also object classes by using this very generalizable affordance segmentation. So far, we have shown generalization of grasps mainly for novel context. We are also interested in continuing this investigation of generalization to novel object instances, object categories, and also maybe skills beyond an object's prototypical use. Our intuition is that we can leverage a knowledge graph encoding semantic relations between objects and tasks as a structure prior to help us generalize the sensorimotor skill of task-oriented grasping. To more systematically study generalization, we introduce task grasp. We increase the number of real objects, the number of grasps, and also more importantly, the number of tasks compared to prior work. We collect RGBD observation, we collect RGBD point cloud observation of each object. We also sample stable 6-DOF grasps from the point cloud. For each valid object and task combination, we crowdsource labels for the grasps. So in total, we annotated more than 250,000 task-oriented grasps for a diversity of tasks and objects. In this figure, we see that these tasks involve both prototypical use of objects, such as using the ladle for pouring, use the paint roller for painting, as well as creative uses of objects, such as using the tongs for stirring or using the ball for scooping. These different tasks impose very different semantic constraints on grasping. Besides the object point cloud and also grasps, we also collect semantic knowledge for the objects and tasks in our dataset. Objects are first manually mapped to word net sets. This allows us to construct a hierarchy of objects. In this example, we see that mug, ladle, pitcher, they all fall under the category of vessels. Furthermore, vessels and spoons, they are containers. In addition, we connect tasks and objects together with use-for relations. In this example, we see that the ladle can be used for mixing, drinking, and dispensing. The dispensing task is also shared with the pitcher object. So these use-for relations help us to connect different tasks and different objects together. Finally, we also leverage word embeddings constructed from ConceptNet. We map objects and tasks to the ConceptNet embeddings in order to get a semantically enriched latent representation of objects and tasks. We hope that the embeddings would ideally capture some of the common sense knowledge that are in this knowledge base. So now we have constructed a knowledge graph and also have infused this knowledge graph with some of the latent common sense knowledge. Now we want to use this knowledge graph, this structured knowledge, to help us generalize the task-oriented grasping. And for that, we introduce a framework for end-to-end learning of task-oriented grasping with the help of semantic knowledge. Specifically, given a grasp in an object, we encode them using PointNet. The resulting embedding is used to initialize the embedding of a grasp node, which we attach dynamically to the knowledge graph. All the other nodes in this knowledge graph are initialized with ConceptNet embeddings, with one extra indicator variable suggesting the goal task. We then use a graph convolutional network to perform message passing. which allows the grasp node embedding to be refined based on semantic relations to other objects as well as other tasks. Finally, the embedding is used to predict whether this grasp is suitable for the context or for the task or not. It's worth noting that this approach does not use any explicit decomposition of object. This is learned directly from the data. We compare with two different baselines. SGN does not use any prior knowledge at all. It learns semantic grasps directly from instance level point cloud data. SGN plus word embeddings use the concept net embeddings that have implicit common sense knowledge about objects and tasks. We report generalization performance at 3 different levels. The result reveals that generalizing to novel object instances may not rely so much on semantic knowledge. That's because object instances within the same object category usually have very similar geometries. Therefore, the variance can be learned by the point net. On the other hand, if we want to generalize task-oriented grasps to object categories, which may have different geometry or to completely new task, robot does need to leverage on the prior knowledge. We also see that the SGN plus word embeddings, which uses implicit distribution alone, is able to outperform the SGN network, which does not use any knowledge at all. However, using structure knowledge as our model help us to obtain an additional improvement in task generalization. So to quickly summarize, in the first project, we use semantic representation to explicitly unify different contextual information. In the second project, we rely on a multimodal neural net to jointly reason about 6-staff grasps, object point clouds, and also abstract semantic knowledge. The use of class-level knowledge also allows the robot to generalize to novel tasks. In the next project, we want to extend the use of semantic and spatial relations to rearrange objects based on language instructions. So geometric organizations of objects pervades the real world. We see stacks of plates in the cabinet, tableware arranged according to the table setting convention, dry fruits placed in a circle. As such, robot would greatly benefit from this ability to recognize and also rearrange objects into semantically meaningful structures. In this project, we focus on the problem of semantic grasping, rearrangement. Given a partial viewpoint cloud observation of a scene and the high-level language Go, we want to find a sequence of actions that transform objects in the initial scene to meet the language goal. Prior work has looked at rearrangement based on visual goals, passively interpreting spatial semantic relations of scene elements for object retrieval or language grounding, and also manipulating pairwise spatial relations to achieve specific target object placement. However, in comparison, we actively rearrange unknown objects into semantically meaningful multi-object spatial structures based only on high-level language instructions, which is also a very intuitive input modalities for untrained users. We treat the semantic rearrangement planning problem as a sequential prediction task and propose a novel transformer-based architecture named structformer. Our system consists of 2 different components. Object selection network is responsible for selecting which object to move by grounding semantic properties in the language, such as colors, materials, and shapes. We obtain latent representation of the objects from the segmented object point cloud using a point cloud transformer. We map word tokens to latent representations using a learned embedding. The latent representation of the language and the objects together are fed into a transformer encoder. Then the output of this transformer encoder is used to predict which object should be moved. The transformer have been shown to be effective at learning cross-modal alignment and as well as performing relational inference. We leverage these capabilities in this network. The post generator is responsible for predicting placement for the objects that are selected by the previous network. by reasoning about the language and also the geometry of these objects. Since we need to generate structures that have multi-object spatial constraints, we propose to use an encoder-decoder structure. The encoder first builds a contextualized representation encoding the semantic content in the language as well as the geometric properties of these objects. This context is then used in this decoder, which auto-regressively predict 6 stop poses of each object in a virtual structure frame, where the pose of this virtual structure frame is predicted first. The decoder factorized the joint probability of go poses for all the objects into conditional probabilities, therefore simplifying the generation of the whole structure into iterative prediction of each object. However, despite this decomposition, our problem still needs to consider constraints on the whole structure. For example, we want to be able to control the desired size for the structure or the placement of the structure on the table. So it's very important to be able to perform this structure level reasoning. And we do this by allowing the decoder attending to the contextual representation created by the encoder. To train StructFormer, we procedurally generate photorealistic and physically valid rearrangement sequences using PyBullet and the render NVC. Each rearrangement is paired with a high-level language instruction specifying both the objects to move and also the target spatial structure. The language instruction contains a diverse set of semantic, geometric, and also spatial concepts. A referring expression can explicitly indicate the query object with a discrete feature, such as rearrange the metal objects, or it can require relational reasoning about both abstract and also continuous properties, such as rearrange objects that are shorter than the glass cup. We generate these rearrangement sequences for 4 different structures: circles, lines, towers, and table settings. These 4 structures test a wide range of reasoning capabilities, such as reasoning about multi-object spatial dependencies for circles or stabilities for towers. The table setting structure in particular requires integrating different substructures, such as aligning cutlery with plates, stacking plates and bowls. For the table setting task, we arrange query objects according to predefined template that follow table setting conventions. Here are some examples of these templates. We use more than 300 3D object models from the ShapeNet to create a diverse set of examples for learning the concepts. In total, the dataset contains more than 100,000 rearrangement sequences, enabling the model to learn generalizable rearrangement policies. I want to now discuss one main experiment from the paper. In this experiment, we compare our post-generation network with several baselines. The binary baseline creates spatial structures by iteratively rearrange each object conditioned only on the previously rearranged objects. No structure is a variant of our post-generation network that directly predicts object poses in the world frame. No encoder is a variant that removes the transformer encoder from this post-generation network. We see from this comparison that our model produces less translational and also rotational errors at predicting object placement for 4 different structures. We evaluated our entire system in simulation environment using 138 novel object models from 23 known classes. On more than 200 randomly generated scenes, StructFormer was shown to be able to rearrange objects into different spatial structures, such as circles, lines, and towers shown here. StructFormer can also effectively condition on the language to place the generated structure on different parts of the table. StructFormer can also reason about the point cloud of the objects to correctly align, stack, and also orient the object to create a diverse set of table setting arrangements. We also deploy the StructFormer on a real robot without any fine-tuning, enabling the robot to rearrange novel real-world objects. The object selection network and the post generation network together provides the user an intuitive way to ask the robot to rearrange desired object into semantically meaningful structures. So in summary, we enable robots to create spatial structures based on language instructions, providing end user an intuitive way to instruct robots. We also show that we are able to generate complex geometric structures by modeling the higher order relations, semantic and spatial relations between objects. So in summary, my research aims to demonstrate that knowledge grounded in perception and manipulation provides robot a unified representation to identify the meaningful patterns of multimodal object properties as well as uses. It also provides robots a structure prior that help robot efficiently generalize sensorimotor skills to novel object categories and also tasks. And finally, semantic representation provides robots an intuitive modalities for humans to command the robots for different spatial semantic tasks. And for that, I would like to thank my collaborators at Georgia Tech, Sonia, the Real Lab directed by Sonia. And also I would like to thank my collaborators from CMU and also at NVIDIA. Thank you so much. I'm happy to take any questions. Thank you.
Okay, thanks, Weiyu, for this great talk. Let me kickstart a question. So on slide 64, you reported like translational error, but also orientational errors. The orientational errors are kind of high. Can you comment on this, why it's so high, or is it even necessary to have like an error of less than 1 degree?
Right. I think part of the reason that the rotation error is very high is because we have a lot of symmetric objects, such as for bowls. Oh, sorry. For bowls or these tall glass cups, they are symmetric, so it's very hard for the model to learn the ground truth. So here we're comparing to the ground truth. But we see like when we test out this model on these real world objects, it's able to learn the correct alignment for other non-symmetrical objects such as forks and knives.
Okay, thanks. Pretty sure we have more questions. Yeah, if you have a question, just unmute yourself and go ahead.
Yeah, I have a question. First of all, thanks for the super cool talk. It's very interesting, like multiple very interesting works. So given that you worked a lot with knowledge graphs, what is your feeling? What is the best way to embed knowledge graphs and in learning problems, particularly if the knowledge graph is given a priori, like from the experience that you had, what would you say would work well or has worked well?
Yes, I think this task REST object does provide a very nice framework for embedding knowledge graph reasoning into learning these different learning other skills, right? And also this framework, a very similar framework has been used for the visual semantic navigation. So in their task, they're trying to retrieve object in a unmapped scene, and they embed their framework with a graph convolutional neural network and to reason about the relations between objects and also locations of objects, and that allows them to achieve better performance. So I do think this is a framework that can definitely be applied to many more things.
Mm-hmm. And here the knowledge graph is basically a priori given, or is it learned in this particular setting?
In this case, it's we crowdsourced this knowledge graph, so it's given a priori. But however, I do think so one of the few extensions of this work is to use the to use a knowledge graph that are constructed automatically from knowledge sources such as concept map. So there is a work that's called Comet. It's from UW, and they are using a neural network to encode all the knowledge in this concept net. And I think it's very interesting to see whether we can use that knowledge, like the common sense knowledge, instead of constructing a knowledge for each specific task. Right? Because
and the resulting graph is it's basically not just a graph of embeddings; it's an interpretable graph, right?
Yes. Yeah. Okay. You can query the network to create. I think this example I'm showing here is the query results of their model. So you can just put the object in interest into the model, and then it will generate these relations.
Cool. Thanks.
Thank you. Thank you for the question.
Hi, thanks for the great talk. And I also have a question regarding this task-oriented grasping. So you have mentioned that is it possible for the network to generalize to novel tasks beyond prototypical use, right? But so for example, sometimes we may use our mouse or even keyboard to do maybe the hammering task because it has a plan, right? So, but does your data set contain such annotations, such non-prototypical use of these objects? Or,
yes. Yeah. So how we collected our data set is first we ask users valid tag and object combinations. So we send out these questions to a lot of users. So if a lot of users think that mouse can be used for hammering, we include that combination in our data set. And then our second stage is to give this object and task combinations and also a specific object point cloud and grasp, and ask the user to annotate whether it's suitable or not. So I think our data set does contain a lot of creative uses of objects, such as, some examples are shown here, like using the tongues for steering, or I think.
I see.
Using the ball for scooping, right?
Yes.
And also here, using the mug for hammering. And also, it's very interesting that the users can also condition on the image and also the point cloud of the object to tell us whether the task and the object combination is suitable. Because if we have, let's say, a ceramic cup, the users may annotate a lot more grasps as unsuitable, because you should not use a ceramic cup for hammering. So that's why I think there are 2 points in our data collection allow us to collect this kind of creative use.
I see. That makes sense. And also regarding the third project, so is the language instruction some structured language, or it can be like free-form language, right? Because I feel like the languages you are showing all have the sentence you are showing all have some similar, how to say, structure or pattern, right? But you are using something like text encoder. So is it necessary to be structured language, or can it just be some free-form instruction?
Yeah. So in this work, we are focusing on I think the spatial side of things. So we use structured language in this case, I think. The short answer. But however, we are exploring how to I guess extend our model to deal with natural language. Yeah.
Yes. Thank you. Thanks for the answer.
Thank you. I guess one thing I do want to comment on is I think the challenge for using natural languages, the users may not provide a very complete language instruction. For example, in this case, we are specifying where to put the circle. However, in a more natural setting, users may just say rearrange object into a circle. And then the robot has to figure out where to put this circle structure, maybe based on other objects in the environment, right? So I think that will be a challenging part for dealing with natural language. Yeah.
Yeah, we have still time for a few more questions. Well, let me ask a more general question. So you presented like 3 lines of work. They look kind of complete. What is the next step, or what comes next? What is like future work?
Yeah, I think one thing I'm very interested in learning, doing is in the first, I guess there are 2 things. The first thing is in the first project, we developed this n-ary relations modeling relations between object properties. However, our this project initially is motivated by the interactive multimodal object perception, and we are not connecting super closely with that perception pipeline. So I think one project that I'm interested in expanding or extending to is to use this n-ary knowledge to guide the exploratory actions of interactive perception. So basically, we want to embed this knowledge reasoning into a sequential decision-making process. So the robot, for example, if the robot has to figure out all the properties of novel objects in the environment, traditionally interactive perception would use all the different exploratory actions, use all the different sensors to extract this huge, let's say, huge set of signals from the object, and then pass them into different networks to do this, to detect the object properties. What we want to achieve is to allow the robot to actively or to intelligently decide which sensor modalities or which exploratory actions to perform next, right? So I think another example is, let's say if the exploratory actions involve dropping an object from some height in order to receive the auditory signal to help you determine the, let's say, the material of the object. If your object is full of water, or if your object is made of glass, you don't want to do that. And I think our network can help us predict that this object is likely to be glass or is likely to be full of water. So you should not use these exploratory actions. Right? Yeah. So yeah, that's one interesting direction I want to explore. And another direction I want to explore is related to this, I think. Yeah, is related to this affordance segmentation. So I think besides this affordance segmentation, there are also other work in like dense object descriptors or in key points. They are trying to create this generalizable object representations for manipulation. And I think, for example, in this case, this affordance segmentation is based purely on 2D. So it does not, I don't think it can capture some of the 3D geometry well, but if there are certain angles of the objects or certain fine-grained geometric properties that are not captured by this affordance detection. So I think that's another interesting idea, interesting direction I want to explore. And also, I think instead of segmenting object into parts, there are times where there are other times where the poses of these parts also matters. So for example, if we are using the pen for for heating water, we should not like just treat the whole handle as one single part. We should also have this notion that closer to the body of the pan, the handle will be hotter, and further away from the part of the body, it will be colder. So the robot should ideally grasp the end of the handle, but that also has to consider like maybe the gravity or the weight of the object. You have to balance different things. So I think develop a more fine-grained semantic representation of objects is another direction I want to explore.
Yeah, interesting. So it has also something to do with object identification. Right. So right now you utilize a lot of images. So there's information about position, but there's no information about like force and so on, like gravity and yes, dynamic parameters. Do you utilize this kind of information right now? Probably with these.
No.
No. And how important is this kind of information in your grasping task?
I think you mean how important is force, that kind of thing in this grasping task?
Yeah, and like the interaction energy if you grasp this too hard or.
Yeah, I think it's very important to deploy this kind of system to real robots. So here's one example. You see that the robot is trying to grasp the handle, but the position of the object kind of slip. That's because we're not modeling that kind of information. So I think it's very important to take that into account. We want to, for example, adjust the position of the object when we grasp it or after we grasp it, right? And I think that's definitely very interesting. So far in my work, I have only looked at spatial and semantic relations. As I mentioned in the beginning, there are other semantic knowledge that us humans possess, such as physics. So in this work, I'm not encoding physics. So I think it would be very interesting to look into that direction as well in the future.
Right. I'm actually very interested in this empty and hot and maybe full case. So how is this model designed? Is it just like it input the network with the visual observation of the object and also input some like text embedding of some concepts like hot, empty, or doing any reasoning?
Sorry, you mean this network?
Yeah, this one.
Okay, so I think I should be more clear, but so from the point cloud, so this is the point cloud of the object. We sample antipodal grasps from the point cloud, and then this is the object detection. So this is the affordance net. Affordance net gives you both the class of the object as well as this affordance segmentation. So we use that to segment the object point cloud, right? And then we use the spectral reading from the biosensor to detect the material. In this case, it's made of plastic. And then so this is the grasp that are in interest. And then we kind of find the part that is closest to this grasp and use the affordance to detect to denote kind of to create the grasp material and the grasp affordance. And then this semantic, so basically these words are fed into the neural network for determining whether,
Well, my question is more like then how can it take the concept like hot into account? Because you cannot know that the liquid is hot if you just observe it. I guess, or if you actually
can. Hot. Okay, I guess that has to go back to this work, right? So and also these prior work. So these prior work allows you to extract different semantic properties using different. different sensors and also different exploratory
Oh,
actions. So let's say if you have an infrared sensor, which we use in this link work, if you have an infrared sensor, you can detect the temperature of the object.
yes,
But
yes, yes.
I guess one of the motivation for this project is also, what if you don't have the sensor to detect hot, but you still want to use the the temperature property? Then you can use our network to, I guess, predict probabilistically whether this object is hot or not hot. Right?
Yes, yes, that makes sense.
Cool. Thank you so much for the question.
Okay, I don't think we have more questions. Thank you again, Weiyu, for this really interesting talk, and for your time, and also to answer all the questions.
Thank you for having me. It's my honor.